All right, so it's me again. Unfortunately, since a speaker had to drop out of the conference, I get the privilege of giving a second talk. So this second talk is called Give and Go with PostgreSQL and SQL. Now, to eliminate the possibility of confusion, when I refer to SQL, I'm talking about the Ruby library. And when I refer to SQL, I'm talking about the database query language. Also, because PostgreSQL is not the easiest thing to pronounce, I'll just be referring to it as Postgres in the rest of the presentation. Now, there's a saying in hockey, don't go through life without goals. And with that in mind, the goal of this presentation is to show off a lot of awesome Postgres features and how you can easily make use of them with SQL. Now, I think one of the reasons that Postgres is not used in more places is that the advanced features that Postgres offers are often not easy to use without good client library support. Now, SQL makes it easy to use many of Postgres' advanced features, and this presentation will separate those features into three main categories. Now, the first category is related to the data types that Postgres supports. Unlike many SQL databases, Postgres supports a number of complex data types, such as arrays, hash tables, JSON, ranges, and composite types. Now, the second category is query types that Postgres supports. I'll be talking about recursive common table expressions, integrated full text search, as well as returning data from insert, update, and delete statements. Now, the final category is really a catch-all for features that do not fit cleanly in one of the other two categories. And I'll be talking about the delayed validation of constraints, prepared transactions, procedural languages, and notification channels. So let's jump right in and talk about some of the advanced data types that Postgres supports. Now, most SQL databases deal with simple scalar types, such as strings, numbers, and dates, and they require multiple columns or references to other tables to deal with combinations of scalar types. Postgres has numerous types that store combinations of scalar types in a single column, which allows you to store more complex data in a single row. Now, the simplest combination type offered by Postgres is the array. A Postgres array type contains an arbitrary number of values of the same type of data, and Postgres supports both single and multi-dimensional arrays. Now, in standard SQL, you would generally store this information in a separate table, but then you need to do a join or issue separate queries if you want to work with the results. And that can be slow for large data sets. By using an array type, you can eliminate joins from your queries, which allows for substantial speedups. Now, depending on the type of queries you are doing, with proper indexes, using arrays instead of a separate join table can be up to 20 times faster. Now, there are a couple of trade-offs you have to make to get such a speedup. One is that your application becomes Postgres specific, and the second is that you need to have support in your client library for the array types. Now, note that these trade-offs apply to pretty much all of Postgres' advanced types, so while I won't mention them again, you should assume that they apply to the other types as well. Now, if you don't have special support in your client library, you'll probably have arrays returned as strings in Postgres array format, like this. You need client library support so that the array types are recognized and parsed correctly into Ruby array-like objects. Now, SQL ships with such support in the form of an extension. If you're just going to be using the array types, you load the PGArray extension into your SQL database instance, and then it correctly deals with Postgres array types. It supports most of the common Postgres array types by default, and you can also register custom array types. Now, SQL also ships with an additional extension called PGArrayOps, which provides DSL support for Postgres array operators and functions. So let's say you were looking for all rows where the array column contains both 3 and 1. You can use the PGArray method to tell SQL that the argument should be treated as a Postgres array, and then you can call the contains method to check that it contains the given elements, and that translates into the SQL that you see on screen. So not only does SQL allow you to treat Postgres arrays as Ruby array-like objects, it also represents the SQL operations on Postgres arrays as Ruby expression objects. And this extends into emulating the Postgres type system. For example, the return value of the contains operator in Postgres returns a Boolean, So the value that SQL returns for the contains method is a Boolean expression. And the return value for the concatenation operator on two Postgres arrays is a Postgres array. So the value that the SQL returns for the concat method is an array expression. And this allows you to chain the methods together intelligently. If you have a row with two array columns, you can see if their concatenation contains both numbers by calling contains on the array expression object returned by concat. Now, in addition to making it easier to use Postgres arrays in your own code, SQL also ships with a model plugin called PG Array Associations, which implements many-to-many associations by storing foreign keys in an array. Now here is the classic join table usage in a many-to-many association. With a table for albums and a table for tags, the association between albums and tags is stored in the albums tags table, the join table, which has foreign keys pointing to both the albums table and the tags table. Using the PG Array Associations plugin, you can eliminate the join table by storing your tag foreign keys in an array column in the albums table. And then it means you can get all tags for a given album without doing a join. Now, the SQL model API for this is almost identical to the join table case, and the plugin handles advanced SQL model association features, such as multiple methods of eager loading, filtering by associations, and dataset associations. Now, unfortunately, the current downside to storing foreign keys in an array is that you lose automatic referential integrity. So you cannot ensure that all of the foreign keys in the array continue to reference existing rows. Now, there have been patches to Postgres 9.2 and 9.3 to add support for array element foreign keys, but unfortunately they were not merged. Now, I'm hoping a future version of Postgres will eventually support them, but it does not seem to be high on their priority list. In the meantime, it is possible to emulate referential integrity for foreign keys that are in arrays by using triggers. Now, the next type I want to talk about is HStore. And the HStore type is a hash table stored in a single column where keys and values are both strings. And unlike arrays, HStore is not a core Postgres type. It ships with Postgres as an extension and is one of the more commonly used extensions. Now, in standard SQL, the general way to represent a hash table is using the entity attribute value model, which is a separate table that has a foreign key pointing to the current row and two string columns, one for the attribute name and one for the attribute value. Now, with proper indexes, using HStores instead of a separate entity attribute value table can be up to 15 times faster. Now, I've used the phrase with proper indexes a couple of times, which is pretty vague. Postgres' advanced types would be mostly useless if they did not have good index support. Now, the hockey great Gordie Howe once said, "You can always get someone to do your thinking for you." And thankfully, Postgres does a good job of thinking for you, supporting multiple advanced index types that you probably would not be able to think up yourself. Now, Postgres has gin and gist index types that it can use to index the advanced data types that Postgres supports. And arrays can be indexed with gin, allowing for index usage with queries where the array contains an entry, a subset or superset of entries, or has any overlap with another set of entries. And HStores can be indexed with gin and gist, and allowing index usage for queries where the HStore contains a key, any or all of a set of keys, or a subset of keys and values. Now, SQL ships with a PG HStore extension for the HStore type, and loading this extension into your database object makes it return the HStore type as a Ruby hash-like object. Similarly, SQL ships with a PG HStore ops extension for DSL support for HStore operators and functions. So let's say you were looking for all rows where the HStore column contains a key of foo with a value of bar. You can use code that's very similar to the array code I showed earlier to do so, just wrapping the column with the HStore method and then using the contains method. Now, in addition to replacing the entity attribute value model, HStores can also combine multiple columns into a single column. For example, if you have 10 columns where the values for most rows are null, you can combine them into a single HStore column for ease of maintenance and potentially better performance. Now, HStores were the first Postgres type that allowed for schemaless design, even if the implementation was limited to just strings. Now what if you want to do a fully schemaless design, similar to a document database such as MongoDB? Now while the merits of a fully schemaless database are debatable, if you do want to go that route, Postgres has a type for that, and that is the JSON type. Now, as you might expect, this allows you to store nested data using JavaScript objects, arrays, numbers, and strings. And the JSON type is a fairly recent addition to Postgres. It appeared first in 9.2, but with many additional features in 9.3 and 9.4. Now, as you might expect, SQL ships with an extension for the JSON type, returning values as Ruby hash-like or array-like objects. Now, a Postgres replacement for a MongoDB collection would look something like the following in SQL. Basically, just a UUID primary key and a schemaless JSON hash for the attributes. So let's take an example of looking at these types in a real application. And this application was called Kairu Era. It's Japanese for frog error. And it's an error aggregator for Ruby web applications similar to AirBreak or AirBit. And it basically logs errors that happen in other Ruby web applications and provides a way to view, search, and track fixes to those errors. Now, as you might expect, the main table in the application stores errors. And using Postgres types, there is only a single row created for every error. And here are some of the fields that are stored. First is the exception class and the exception message, which are both stored as plain strings. Then there is the backtrace for the exception, which is stored as an array of strings. It also stores the request environment, which fits nicely into an HStore, since keys and values are generally strings. And finally, it stores the request params and session variables as JSON, since they often contain nested structures. Now, without the advanced types supported by Postgres, storing similar information in any sort of structured or queryable format would probably require inserting hundreds of rows across maybe 5 different tables. Now, you may be wondering why you would want to use an HStore type if you could use a JSON type, since the JSON type supports nested structures and the HStore type does not. And one reason is that there is no automatic indexing support for the JSON type, unlike the HStore type. You can still create indexes based on a specific member of a JSON column, even a nested object member, but you have to create specific indexes for each type of search. And note that these trade-offs are going away in Postgres 9.4. Postgres 9.4 introduces a type named JSONB, which can store JSON data, but in a way that allows it to be indexed with GIN and GIST indexes. So you get all the flexibility of JSON, but with all the performance of HStore. And SQL 4.11, which will be released in a few days, will add support for this JSONB type. Now, I mentioned earlier that Postgres added a whole lot more capabilities to JSON in 9.3 and 9.4. And those capabilities were in the form of additional JSON operators and functions, most of which in 9.4 operate on both the JSON and JSONB types. Now, SQL's PG-JSON-ops extension adds DSL support for these new operators and functions. So let's say you were using the JSON displayed here and storing it in a JSONB column. If you want to search and see if that JSONB column contains a key A with a value of 1, you can wrap the column with PG-JSONB, and then you can call the contains method with a hash used for search, just like when you're using HStore. Now, what if you want the benefits of having nested data in your row, but you want the consistency benefits that come from using a defined schema? Postgres supports this with composite types, where a single column contains a data structure with multiple subtypes. And when you combine composite types with the array type, you basically have the power to store full documents with unlimited nesting in a single row. Now, Postgres allows for user-defined types with the create type syntax, which is very similar to create table. It takes a list of columns in the type. And additionally, for every table you create with create table, a corresponding type is created. So let's say you have a music database, and you want to store each album in a single row, including the full track list. And a typical JSON representation would look something like this, storing the name and length of the album, and then an array of tracks, with each track having a name, length, and reference to the related artist. Here's how you could structure the data using Postgres arrays and composite types. You have a separate track type with a name, length, and reference to the artist. Then your albums table has a column for the name, a column for the album length, and a column containing the track list as an array of track types. And this approach allows you to keep an entire album, including all tracks, in a single row. It combines the benefits of a document database, getting the object in a single joinless query, but still retains the data consistency benefits that come from using a defined schema. And I actually use a design similar to this in one of my applications, though for a slightly different reason. I'm sure most of you have heard of Heroku, the platform as a service provider, and one of the many benefits of Heroku is that they offer a completely free way to run low-traffic web applications, including a free Postgres database. Now, when Heroku first started, this database was limited to 5 megabytes of data. And a couple years ago, they switched from 5 megabytes of data to 10,000 rows of data. Now, at the time, I had an application that was over 10,000 rows, but had less than 5 megabytes of data. And it stored tracks in a separate table from albums with 1 row per track. Using an array of composite types, I was able to eliminate the separate tracks table and just store the tracks inside the albums table, getting me under the 10,000 row limit. And I was able to do this while increasing performance and still allowing for indexed querying by track name using Postgres' advanced indexing features. Now, Postgres allows you to combine the schemaless and relational approaches and get the benefits of both worlds, using a defined schema for the columns that you know you need, but still having a schemaless JSON or HStore column in the cases where you want to trade consistency for flexibility. Now, SQL ships with a PG row extension that enables composite type support, returning values as Ruby hash-like objects. And additionally, SQL also ships with a model plugin called PG row, which allows you to represent composite types as SQL model instances. And the final Postgres data type I'd like to talk about is the range type. Now, range types in Postgres are similar to Ruby ranges, but they are a little bit more flexible. For example, Postgres ranges can be unbounded on either end, and they allow for exclusive beginnings, which Ruby does not allow. Now, Postgres has built-in support for numeric, date, and timestamp ranges, and it also allows you to define your own custom range types. SQL ships with a PG range extension that enables support for range types, returning Postgres range types as Ruby range-like objects, and allows you to use Ruby ranges to represent range types in your queries. And to make using Postgres ranges easier, SQL also ships with a PG range ops extension that adds DSL support for range operators and functions. So let's say you have a hotel reservation system, and you want to see which reservations include today's date. You could use something like the following code. And by design, it looks very similar to the HStore array in JSONB code, just wrapping the object with PG range and then using the contains method. Now, range types by themselves are only marginally useful, since they can be emulated by using separate columns for the beginning and end of the range. However, there is another Postgres feature that makes range types very useful, and that feature is exclusion constraints. Now, exclusion constraints are similar to unique constraints, but instead of protecting against duplicate values, they protect against overlapping values. So for any work where overlapping values are not allowed, such as when you're scheduling access to a limited resource, Postgres exclusion constraints are probably the best approach to the problem. So let's say you want to book a reservation for room 1 from May 30th to June 1st. And assuming nothing else has already reserved room 1 in this time period, this should work correctly. Later, if something else tries to reserve room 1 from June 1st to June 3rd, it will fail because that overlaps with the existing reservation from May 30th to June 1st. When the exclusion constraint fails, SQL will recognize it as an exclusion constraint violation and will raise a specific exception class. So then you can then rescue this exception class in your application code and be confident that the exclusion constraint is what caused the error. You can then alert the user that the room is already reserved during that time frame and offer to book a different room at the same time or the same room at a different time. So let me briefly review the types I discussed. First was the array type, good for keeping multiple instances of the same type of data instead of using a separate table. Next was the HStore type, for keeping simple attribute keys and values in a single column. Then I talked about the JSON and JSONB types for fully schemaless documents. And then talked about composite types for the nesting benefits of using documents, but with the data consistency benefits that come from using a defined schema. And finally, I talked about range types and how using them with exclusion constraints can make it much easier to protect against overlapping values. So that brings us to the second part of this presentation, where I'll be talking about some of the advanced query types that Postgres supports. Now, the first type of query I'll be talking about is the common table expression query. Now, a basic common table expression is just a way to give a subquery a name for the period of a single query. It's sort of equivalent to defining a temporary view. Now, in this example, we were creating a subquery called current reservations, which selects the rows in the reservations table that include the current date. This outer query then selects from that subquery and then joins it to the rooms table. Now, in this example, this does not give you any additional features that you did not have before, since you could just filter the rows in the main query. So why did I spend time discussing this? Well, it turns out that while basic common table expressions are uninteresting, they have a very interesting variant. And that variant is the recursive common table expression. A recursive expression has similar syntax to a basic common table expression, but it recursively queries itself using the output from the previous iteration as the input to the following iteration, and when no more output is produced, it returns the combined output from all iterations as the result set of the view. That's hard to reason about abstractly, so let me provide a concrete example. Here is the simplest possible recursive common table expression that I can come up with. Note the use of recursive to signal that this is a recursive query. Now, this query will return 10 rows with a value starting at 1 and ending at 10. And let me break down how it works. First, as you can see here, recursive expressions are broken into two parts separated by a union. The part before the union is referred to as the base case and cannot refer to the recursive expression internally. The part after the union is the recursive case, and when it refers to the recursive expression, for the first iteration, it receives the output of the base case, and on future iterations, it receives the results of the previous iteration. This continues until the recursive part produces no output. So here's the base case, and this is pretty simple. It just returns a single column with the value of 1. And here's the recursive case. Now, the first time the recursive case runs, the value of a.b will be 1, since that is what the base case returned. Since a.b is less than 10, this will return 1 row with a value of a.b plus 1, which is 2. Since it returned output, another iteration will run, this time where a.b is 2. And these iterations will keep running until a.b is 10. Now, when a.b is 10, the recursive case will not return any rows, at which point the recursion stops. When the recursion is finished, all output from both the base case and all recursive case iterations are combined into a single result set, which is returned. And that result set in this example will be all numbers between 1 and 10. Now, if a simple counter is fun, surely using a recursive expression to return all Fibonacci numbers under 100 is even more fun. So you can do this by iterating using 2 columns, where each iteration returns the larger number and the sum of the 2 numbers in the previous iteration. Now, these examples might be a little bit too simplistic, so let's move on to a real example. So let's say you are using the reservations table that we discussed earlier, storing a date range. You get a new 5-day reservation, and you attempt to save it, but it turns out it overlaps with an existing reservation, and an exclusion constraint violation is raised. What should you do? Well, to be helpful to the user, you may want to scan the reservations table to try to find the next available 5-day reservation that does not overlap with an existing reservation. And how can you do that? Well, if you guessed using a recursive expression, have the person next to you pat you on the back. Here's example code that does that, and while this is obviously a fairly complex example, I will try to break down how it works. As usual, we'll start with the base case, which returns 2 values. The first value is the date to start looking for reservations, which in this example is the current date. The second value is the starting range of dates that we are looking in, which for this example is the 5-day date range starting with the current date. To test for overlap, in the recursive case, we create a 5-day date range using the starting date returned by the previous iteration. And to test for overlap, use a subquery on the reservations table, comparing the date range we created in this iteration to the existing date ranges in the recursive dates column, reservation dates column. We select two values in the recursive case. The first value is the maximum upper bound of any overlapping date range. So if there is overlap, this is the starting point for the next iteration. And if there is no overlap, this will be null. We choose this value because it allows you to skip over all days inside the overlapping date range, which we know must also overlap. We also select the new date range that we use to test for overlap. And on the next iteration, if there is no overlap from the previous iteration, the where clause evaluates to null and the recursion will stop. And we limit our search to 30 days in the future so that it only searches the time frame we are interested in. When the recursion stops, the common table expression will return the rows used for all iterations. Now, the only row we care about is the one where there is no overlap, which is when the first value is null. So we filter for rows where the first value is null, and we select the second value, which is the non-overlapping date range. Now, the advantage of using this approach to find open reservations is that it is fairly fast as it runs completely on the server. It skips unnecessary testing of date ranges that we know would also overlap. It returns as soon as it finds an open reservation, and it's probably easier than writing a function in a database procedural language that would do the same thing. Now, as you've seen in the previous example, recursive expression syntax can be somewhat complex, and it does take some time to learn how to write recursive queries. However, as hockey great Bobby Orr used to say, forget about style, worry about results. Well, SQL doesn't always forget about style. It offers helper methods for writing these recursive queries. And the SQL in the previous example was not written by hand. It was generated from this SQL dataset. SQL has a withRecursive method that is used to generate recursive expressions. You pass this method the name of the recursive expression, a dataset for the base case, represented here with a red background, and a dataset for the recursive case, generated here with a white background. Note that this SQL code is more concise than the SQL that it generates because it is able to reuse expressions. For example, there are 3 calls in the SQL to create a date range, but the SQL code just has 3 calls to the same proc. It's also easier to change the starting date or the number of days in the reservation by modifying a single value instead of modifying the values in multiple places in the SQL. The previous examples I've given have not shown this, but recursive expressions allow Postgres to run the same types of queries that you would previously use a graph database for. And you can write queries that traverse trees and graphs and return all related objects. Now, SQL ships with a model plugin that uses recursive expressions for tree traversal, and it's called RCTE tree. You load this plugin into your model class, and it adds methods to load all ancestors or descendants for a given node or a set of nodes in a single recursive query. If you call the descendants method, it runs a recursive query similar to this. Now, the base case starts by selecting all children of the current node, which are nodes where the parent ID is 2. And the recursive case selects all children of the output of the previous case until there are no such children. SQL even has the ability to eagerly load only the first few levels of descendants instead of loading all descendants. And this can be a good middle ground between loading all descendants at once and loading each level of descendants in a separate query. Now, this query is similar to the previous query, except that we are keeping track of the root node separately as we are eagerly loading, and we are incrementing the level on each iteration and only returning results up to the level selected. So is anyone here familiar with nested sets? Okay, a couple guys. Using recursive queries to load trees allows for basically all of the features of nested sets, but it has much simpler storage, a much simpler implementation, and is orders of magnitude faster in many use cases. So the next query type I'd like to discuss is the use of the returning clause. And unlike standard SQL, where only select can return rows, Postgres supports the returning clause on insert, update, and delete statements, which selects the rows that are inserted, updated, or deleted. For example, if you want to insert a row into the table and have the values of the inserted row returned, you can use a query like this with returning star. And this is useful as it automatically returns the default values set by the database. And while you could get this information separately using a select query, this combines the insert and select into a single query, which is faster and avoids race conditions. Now, by default, when you create new model instances, SQL will use the primary key of the inserted row to retrieve the inserted row values with a select query. However, since Postgres supports returning, SQL does the insert and select in a single query that uses returning star, which speeds up all model creation automatically. Additionally, SQL datasets have a returning method, allowing you to specify which columns to return in insert, update, and delete statements. And this allows you to express the previous SQL query as a simple dataset. You can use the syntax to do things like updating archive tables by automatically inserting rows deleted from one table into another table. So this example uses a common table expression with delete returning and has the outer query insert the output of the common table expression into an archive table. The last query type I'd like to talk about is full text search. Now, unlike most SQL databases, Postgres has good built-in support for full text search with full transactional support. Take that, MySQL. Here is the basic full text search query in Postgres. You wrap the column containing the text to search in a TS vector and the terms you are searching for in a TS query, and you use the @ operator to perform the search. Now, the first argument to these functions is the language you want to use for the search. Now, since this is pretty ugly, SQL attempts to simplify it for you. SQL has a full text search method that takes the column to search, the search terms, and accepts the language as an option, so you do not need to specify it twice. Now, one of the best things about full text search in Postgres is how flexible it is. If you remember the Cairo error example I discussed earlier, let's say you want to add full text searching to the backtrace column, which is an array, and the environment variable column, which is an HStore. You can convert the backtrace array to a string, and the environment variable HStore to an array and then to a string, and then you can do full text searching on the concatenation of those two strings. Now, all of those conversions are going to be slow for large numbers of records. To speed it up, you'll have to add an index. And adding a full text index in SQL is very easy, since the syntax is very similar to the syntax you use for a full text search. Now, the great part about this is you do not actually need to store the string containing the concatenated full text of the backtrace array and the environment HStore in a column, which saves you space and makes querying faster and easier. And once you've set up a full text index, full text searches are generally pretty fast. So let me briefly review the query types I discussed. First is the recursive common table expression, allowing for incremental scanning of tables and efficient traversal of trees and graphs. After that, I talked about the returning clause, used to return rows from insert, update, and delete statements. And finally, I talked about the advanced full text search features offered by Postgres. That brings us to the final section of the talk, which will cover some other interesting features of Postgres. Now, the first feature I'm going to discuss in this section is the defining foreign key and check constraints with delayed validation using not valid. Now, not valid constraints fix a long-standing issue, which is that when you're adding a constraint to an existing table, it requires a table scan and a lock to ensure that the constraint is not violated, and if any row violates the constraint, adding the constraint fails and you have to try again. During the table scan, the table is completely locked. However, when you mark a constraint with not valid, the table scan and the lock are not done. The constraint is still enforced for all new rows and all updates to existing rows, so you can be sure that no new invalid data is introduced. So after adding the constraint with not valid, you can clean up the existing invalid data by updating invalid rows so that they no longer violate the constraint. After you have removed the invalid rows from your table, you can then validate the constraint later using validate constraint. And this still requires a table scan to ensure that existing rows do not violate the constraint, but it requires a lesser lock on the table. Now, SQL supports both of these syntaxes with a not valid option when defining constraints and a validate constraint method for validating them later. So the next feature I'd like to discuss is the use of listen and notify to send and receive messages on notification channels. And this is basically a self-contained inter-process communication mechanism inside Postgres, where database clients can send messages to each other. And one of the most common uses for this is to notify clients when data has changed. For example, you can add an insert trigger that uses notify to notify a channel of all inserted rows with the primary key of the inserted row. And then you can have another process that listens for those notifications and acts on them. So let's assume you have added such a trigger, and you want to automatically tweet every time a player is added to your favorite team. You can use SQL support for listening on channels to receive notifications on the players table and then automatically tweet the results. And there are a couple of things to note here. First is the arguments to listen, first of which is the notification channel name. And this can also be an array if you want to listen on multiple channels simultaneously. The second argument is the options hash. And in this case, the loop option is used so that you continually listen for notifications, yielding them as they come in. Now, the second thing to note is the 3 arguments that the block receives. The first is the channel that the message was received on. The second is the PID of the background process that generated the notification. And the third is the payload of the message notification, which in this case we assume is the ID of the player added. After we receive the notification, we need to check the players table to get the information on the inserted player. And since we only care about players that join our favorite team, we need to check if the player has that team ID. And if so, we tweet that player joined our favorite team. Now this is a fairly contrived example, but a similar approach can be used to solve a very real problem. Now Phil Carlton, in addition to having an awesome mustache, working on X11, and playing roller hockey, was also famous for saying that there are only 2 hard things in computer science: cache invalidation and naming things. And while this is obviously a tongue-in-cheek comment, it is telling that of all the hard problems he could pick to stand next to the punchline, naming things, he chose cache invalidation. It turns out that the combination of listen and notify is actually great at handling cache invalidation. You have a trigger that uses notify whenever a table changes, and then you have your caching application use listen to be notified whenever changes are committed so that you can modify the related cache. Now SQL ships with a model plugin called static cache that caches entire small and infrequently updated model tables so that many common model operations do not require database queries. Historically, the static cache plugin could only be used if the underlying model table was never updated at runtime. However, last year I added an option to the plugin which allows the table to be updated at runtime, but it requires the user to manually reload the cache in that case. To make this easier on the user, SQL ships with a PG static cache updater extension, which makes it easy to define triggers on the underlying model tables that use notify to signal changes. It also has a method that creates a thread in your application that listens for changes so that anytime the underlying database table for a model changes, all of the application processes automatically update their in-process caches for that model. So while naming things is still hard, cache invalidation becomes a little bit easier. So the next feature I'd like to talk about is prepared transactions. Now prepared transactions are also known as two-phase commit and are used in distributed database transaction to ensure that either all sides commit or none of the sides commit. With distributed databases, using a regular transaction is not sufficient. You cannot commit before receiving confirmation from the other database, since the other database may not commit, and then you can no longer roll the transaction back. You cannot wait until after receiving confirmation from the other database to commit, because there might be a deferred constraint validation or violation, or some other issue that causes the current database to roll back. And in either of those cases, the 2 databases would be out of sync, and that is a bad situation to be in. It just so happens that SQL has full support for Postgres's prepared transactions. So to create a prepared transaction, you use the prepare option to SQL's transaction method. And the value for this option should be the transaction ID string related to the current transaction. Then you just write the rest of the transaction code like you would normally. The difference between a prepared transaction and a regular transaction is that after the transaction block ends, it appears to the outside world that the transaction has not been committed. However, the locks required by the transaction remain in effect, so you cannot do things that will cause the prepared transaction not to be committed. After you have received confirmation from the other side that the transaction has been committed, you can call commit prepared transaction with a transaction ID string to commit the transaction you just prepared. If for some reason the other side was not able to successfully commit the transaction, you can roll it back on the current database using the rollback repair transaction method. And this ensures that the two databases are kept in sync. So the final feature I'd like to talk about is Postgres' support for procedural languages. Now, unlike most SQL databases, which support a single procedural language or maybe two, Postgres supports many different procedural languages. Here are just some of the procedural languages supported by Postgres. The languages in red ship with Postgres, and the ones in black are available as external downloads. And hopefully, some of these languages here are familiar to you. Unfortunately, as you can see, I put a line through Ruby. While there is support for using Ruby as a procedural language, in my experience, it is not stable and should not be used. Another interesting feature is the ability to automatically execute anonymous functions at runtime in a procedural languages without defining them separately using a do statement. So naturally, SQL supports this using the do method. And here's an example that uses an anonymous function written in the PL/PGSQL procedural language. And it does this to insert a row. Now, who wants to get a little bit meta? Let's say you want to have your anonymous PL/PGSQL function call an anonymous function written in Perl to insert the row. Or have that Perl function call an anonymous function written in Python. Or have that Python function call an anonymous function written in JavaScript. Or even have that JavaScript function run some shellcode. So I've tested this, and this actually works. This is an anonymous PGSQL function calling an anonymous Perl function, calling an anonymous Python function, calling an anonymous JavaScript function, running some shellcode that uses the PSQL program to insert a row into the database. And the hardest part of this is getting the quoting correct. This makes extensive use of Postgres dollar quoting, which is similar to, but more flexible than Ruby here.doc syntax. So that finishes up the final section of this presentation. Let me briefly review what I talked about. I talked about adding constraints and delaying validation until after you've had a chance to clean up existing invalid rows. I talked about the use of listen and notify for simple inter-process communication and cache invalidation using Postgres notification channels. I talked about using prepared transactions to keep distributed databases in sync. And finally, I talked about Postgres' support for many procedural languages and using anonymous functions written in those languages. So that pretty much covers all the Postgres features I wanted to talk about. I'd like to leave you with a quote from probably the greatest hockey player, Wayne Gretzky, who said that a good hockey player, he plays where the puck is. A great hockey player, he plays where the puck is going to be. And when you're designing an application where the data actually matters, when it comes time to choose a database, you cannot just think about today. You have to think about many years in the future. In any situation where the data you are dealing with is important, your database will probably last longer than your application. Over the last 10 years, I've watched Postgres get better and better every single release. And I fully believe Postgres is the best database choice for most applications. And if you're writing your application in Ruby, that SQL is the best way to access it. And hopefully this presentation has shown off a lot of cool things you can do with Postgres. If you have any questions for anything I've covered, I'll be happy to answer them now. Thank you.